Okay, we're going to be working with angular velocity, linear velocity a lot. So, let's just make sure we actually know what these terms are before they start getting thrown around. To the best of my abilities. We work with linear velocity a lot. It's like we kind of know what it is, but what is angular velocity? Angular velocity, like I said, angular, right? It's velocity in relationship to some angle, not in relationship to linear distance. So angular, we're going to be talking about, we're going to have some angle. So let's just think about this on a circle, right? Angular velocity is in terms of radians, right? In terms of this circle. So let's say we have a path here and there's a coin or a rock or whatever, some object here and some object here. And let's say, the line that they're on is moving, right? They're both on this line that's moving. So like later on, the line ends up here. They're both still going to be in that same position. From here to here, or actually, let's get rid of this. From here to here, that's what, like 45 degrees? So remember, this line, it's moving. So they're moving at the same time, right? To get to 90 degrees. When they reach that, to reach that 45 degrees. Once they reach these two objects, once they reach that 45 degrees, they've covered the same amount of time, right? If I have something at the end of here, something at the end of here, and I go like this, it's been the same, second? They're at the same angle now. That's angular velocity, right? These two objects are always going to have the same angular velocity. But linear velocity is going to be different because the distance that this one covered is much less than the distance that this one covered, right? If we're thinking about it in terms of a linear distance. This one covered less, this one covered more. So this one on the outside is going to take longer or travel a longer distance than this one is going to travel. Right? And it's covering a longer distance over the same amount of time. Because remember, this thing, it's moving at the same time. So they're moving at the same amount of time. But the one on the outside is actually covering more linear distance than this one is. Therefore, this one has a greater linear velocity. Their angular velocity is the same. Their linear velocity is different. Hopefully that makes sense. We have some equations up here to help us where if we know our angular velocity, we can calculate our linear velocity by the equation I wrote up there. Linear velocity is your angular velocity times your radius. And as you can see here, the radius for this, for these two objects is going to be different, right? The angular velocity is going to be the same. This one has a shorter radius. This one has a longer radius. You plug in a bigger R value, you're going to get a bigger velocity. So that's just another way of proving this one's actually going faster. And if we're given something like RPMs, like in the last problem we had 80 RPMs, we can calculate the linear velocity by that equation. Linear velocity is equal to 2 pi times whatever your RPMs are over 60 seconds. That will give you your angular velocity, which you can then multiply by the radius to get the linear velocity. Or you can just use the equation, the velocity is 2 pi r over t, where t is not the time. T is equal to the time over the number of cycles. So remember, if you want to use this one, you just have to remember t is the time over the number of cycles. In this equation, or in this example, we're going 1 minute per 80 cycles, because one cycle is one revolution, 80 revolutions, right? And then, since it's in minutes, we want it in SIs. 1 minute is just 60 seconds, though. If it were, 90, you just do 90. Whatever you want to do. But yeah, that's the difference between angular velocity and linear velocity. Hopefully that makes sense. Just wanted to cover that really quickly if you didn't already know.